All right, hello everyone. So this is the last class of our 8-course programming class. Oh, don't worry about it. All right. Hello there. Okay, so the past 7-ish classes, we've mostly been talking about like actual coding, specifically things about coding, the various objects, methods, and functionality you can create inside a program. Things like for loops, which allow for repetition, and if loops, which allow you to change your program's function based on a true or false question. And using these, you can essentially create many different programs, because these are like essentially the backbone of what most programs and games are made out of. Repeating various tasks, such as checking if a character is moving, or checking if a user is clicking on a specific piece of input or not. So today, what we're going to do is we're going to talk about stuff that is a bit detached from coding itself, specifically various methods and stuff that you can use to improve coding. Today, we're going to be talking about two main things. That is sorting, searching, and sets. So let me share my screen real quick. All right. So we're going to start. So searching is essentially just searching. Specifically, given a list of data, how do you go through the entire list of data and pick out, say, a specific value or multiple specific values? You already know one way, which is with a for loop. Or in other words, if I gave someone a list of values, and you want to look for, say, the specific value 5. In order to program, one way that we've already discussed how to do is with a for loop, where, again, with the repetition, you would go through every element in the list one by one and use an if function to check whether or not it matches. Say if we're looking at the value 5. So this is the most basic search that we know. Essentially, you go through every single element in a list, and if one of the elements matches what you're looking for, then you print it out. Or say if you're looking for the largest value and the list is not sorted, so you can't just go to the end of the list. So like, looks like this. Then in order to look for that, you would simply have to say, to find the biggest value, you would again have to go through every single element, and then simply check. And then simply record down the relevant data. So you wanted to say find a maximum value in a set of data, you would have to first of all find somewhere to store it. So in this case, we store the maximum value in a number container called max, and then we store the position in a number container called index, which is the index or position of the max value. We go through every element, and if the element we are currently looking at is ever greater than what we have recorded as the maximum value, we replace the maximum value with this new maximum value, and then we simply print it out at the end. So this is the first type of searching, which is essentially just looking at every single element until you either find the correct element or you reach the end of the list. Another method of searching for more complicated lists will be, there are also other different methods of searching. For example, let's say you had a list that was already sorted. So in other words, the list already had all the values are in like numerical order, or you knew what order they were. Like you knew the list was going to be from biggest to smallest to biggest. Then there are other techniques you can use to make it so that you can find the value extremely quickly. The one we're going to talk right now is called binary search, which only works on a sorted list. If it's an unsorted list, the only real option you have is to go through every single element, because again, if it's unsorted, that means there's no pattern to the elements, which means that there's no way to formulaically decrease the amount of time it takes, since in the worst case scenario, you're still going to have to search every single value. But if the list is sorted, we can decrease that time significantly by implementing a binary search, and binary search essentially works like this. It's like if you're playing one of the guessing number games, you usually start in the middle. And then then they tell you whether the number is bigger or smaller. And if it's bigger, if the number you guess is too big, you move to the small number. And if it's too small, you move to a bigger number. Binary works the same way. You pick a number in the middle. In this case, the number in the middle would be the length of the list divided by 2, which would give you the middle number. And you can't use a for loop this time, because the number of times it's going to run is going to change depending on how lucky we get, essentially. Where this program is created in such a way that it won't have to look at every single value. So in this case, we would have to do a while loop, which is essentially just while our maximum number does not equal the value we're searching for, let's say 8. And all you have to do in this case, you would simply go if the current value at list.index is greater than what we're looking for, then we tell index that it's, because remember, we're looking at a sorted list this time. So this means the index must be looking at a number that's too large, which means that we go backwards, or depending on how it's sorted, it might change. Otherwise, if it's less than, okay. So essentially binary search, well, technically this is the binary search, yeah, since it doesn't quite have it each step. This is simply a quick search, which essentially just starts at the middle and then continuously increases or decreases depending on how far away your guess is. Binary
Hello.
search would be having to, oh, hello.
Hello.
All right.
I have a question.
Yeah.
Did you post like the videos for like?
Oh, I haven't yet. I was going to do that.
Oh, okay. Yeah, I was gone
about
for a
that.
camp, so I couldn't attend the class.
Don't worry about it. I will put them on today.
All right, thank you.
Yeah. Today we're going to talk about various techniques, because we already talked a lot about essentially coding stuff. So now we're going to talk about how to actually apply that. And specifically right now we're talking about searching, which is given a list of values, sometimes randomized, sometimes sorted. How can you quickly find the correct value? In an unsorted list, you have to go through every single value on the list. There's no fast way to do it, since an unsorted list is random and there's no pattern to a random set of numbers. However, if you ever get a sorted list or any list with some sort of pattern to it, then you can cut down your search time quickly. Specifically in this case, we're looking at a sorted list that increases. And we're using what's called a binary search, which halves the number of stuff when you look at each step. So yeah, so essentially we first pick the index in the middle of the list, and then start at the very middle value. And if this middle value is too big, then we set the new index to a different value. So in this case, it would be the halfway point between our current point and 0, because this point is too big. So we need the middle value between the too big point and the smallest possible point. The index is not equal to index divided by 2. Technically, this is index plus 0 divided by 2, but since it's plus 0, you don't have to write that. And then finally, we have to set max. We actually need to change this real quick to actually check the value. And then if it's too small, that means our value must be between this too small value and the maximum value. So index must be set to index plus the length of the list divided by 2. And by this way, we have our search error at each step. which allows us to find whatever value we're looking for much faster. These are the two main searches that you'll ever use. There are other searches, but binary search is like already incredibly fast. Most of the time, searches won't be the biggest source of won't be the biggest source of time saving, but especially in sorted list and with large values, a binary search can often save a lot, actually decent amount of time, just not as much as some other things. Yeah, so if essentially an unsorted list, you have to go through every value, but a sorted list, you can use a variety of techniques. The best one is to do a binary search, which is fast because it has the search amount at every step. Hello. Okay, so we were just talking about searching techniques, or essentially how to use a computer to search through data to find a specific value. And in an unsorted list, you have to use a for loop that goes through every single data point. But if the list is ever sorted, there's a pattern. You can use different searches. And the one we were talking about, the fastest one, is binary search, which essentially just goes to the middle of the list. It picks an index that's in the direct middle. And then every time this index is not equal to the value we want, in this case, we just set it to 8 as an example. We check if the current value is too big, we know the number has to be between this index and 0. So we simply half this index. And this index is too small, then we know it's between this too small index and the maximum value. So we add so we go to the middle between these two values. We repeat until we find the correct index, at which point this loop will end. Of course, one thing to watch out for is in this specific implementation, what I didn't write just yet is that this doesn't check for an infinite loop. It's possible that your list does not have the value 8, in which case you'll have to account for it through someone. For example, probably the best way to do this is if you ever repeat checking an area, then that means you have repeated, or you can simply check the value above and under it every step. And if the value above or below it precludes 8 as an answer, then you also would have to break at this point. So for example, if so in this case, because we know that our current value is greater than 8, and we're going to a value less than that, we have to simply check if this value if this value isn't valid anymore. Yeah, so in this case, what we did was we added each index we check to the an array list, which can hold up, which is essentially another way of storing numbers. Sorry, not numbers, data. But this specific array list is meant to store integers. So. Yeah, so. Yeah, and so essentially, if the ever comes and it basically it's go and we check the array list, and if it ever contains the index we just looked at, then it breaks out the while loop, and that's when we know. And if it ever breaks at this area, that's when we know that the value does not exist. Because if we ever repeat a step, that means we've essentially gone backwards, and that means it's gone between the two numbers that should contain it but don't. There are also other methods to check that are a bit more pretty than this, but this is the main one essentially. Now, in most programs, especially competitive programs, one of the much more larger time wasters is sorting, or when you have to sort a list of data into however they want you to print out. Usually say sorting a randomized piece of data into an increasing set of numbers. The intuitive way of solving it would be with a bubble sort, which essentially just looks at two numbers and swaps them if they're in the wrong position. So this is bubble sort, which is the fastest, right? But is also one of the slowest. So the way bubble sort works is it uses two loops. And every time it loops, it compares the value located at I and value located at J. And then it simply goes, if the list at I is less than J, because I is always going to be either equal to or less than J, since J always increases first and is at a minimum equal to I. So in other words, J should be larger if you're trying to sort it from smallest to biggest. But if it's ever not, then we simply swap them using this piece of code here. We first store I into a temp container, because if we don't, then the value at I will be it'll be gone when we replace it with the value at J. So in other words, if we did this and then try to do this, what do you think is wrong if we try to swap it like this? What do you think is the error here? Yeah, so yeah, exactly. So the error here is that when you, let's look it up through one line at a time. When you do this step, the value at list J is we're going to replace the value here, right? But since we're using a single equal sign, also known as the assignment operator, the value to the right is assigned to the container here. Or in other words, the original value here is completely replaced. It's gone. It gets erased, and then it gets filled in with this new value. So if you try to do this instead, it's going to look at the value in list I, but the value in list I is the value that used to be at the J position. So in other words, these two are going to become the same number, which is not what we want. We want the original value of list I to be here. I can't just switch the positions around because that will lead to the same issue again. But what we can do is simply take the list value list I, place it inside a temporary storage variable. In this case, it's really just called temp, which holds an integer. And then we want to replace the value of list J. We use temp, which has not been, which is equal to this value and has not been changed, unlike list I itself. So this will allow us to switch the two numbers around. And then this will go through every single two-pair combination and will eventually sort them together. However, because this uses a double loop and one of them is nested inside the other, it's pretty slow. There are many other methods which I encourage you all to look for, but the most common ones involve insertion sort, merge sort, and quick sort. So they're all pretty different from each other, and they're all much faster than well, they're all decently faster than the bubble sort we're talking about right now. The fastest one is known as merge sort, which essentially goes like this. You take a list, and then you keep dividing it into two halves until you get a list of value 1, and then you join them back together, join all of these individual half lists back together swapping every time you see every time they and then sorting each of these small individual lists instead. And because we're sorting multiple small lists, it's much faster, but it's also incredibly complicated to code. A more common one to use is Merge Quicksort, which works with recursion. So recursion is a pretty big thing. Recursion itself is really slow, and you want to avoid actual recursion, but the idea of recursion is extremely important and is used in things like dynamic programming. So recursion, and sometimes recursion is impossible to avoid, but most of the time you use it as the basis of an idea and not actual part of a code if you can avoid it. So recursion, which is an essential part of Quicksort, works like this. So the way recursion is post a function is essentially it's a method, like the one we're doing here, that's supposed to call itself. For example, in the this example one is called Fibonacci, and it's going to find the essentially all the values in the Fibonacci number. And so in order to find the values in Fibonacci works by adding two previous values together. And so, and like it would, and every time you add the two previous numbers, like contributes to the next number in the list. So essentially, since A, I'm doing that. Okay. So, okay, so as you might see here, this method Fibonacci is calling itself when it's trying to give you an answer. So if we put, say, the value 1 here, it wouldn't reach this step. It would the if function here would first fulfill true. It would reach this step, and then as soon as it sees the return, it automatically return that value and stop there. Remember, a return in a method automatically stops the method there because it's already reached its necessary output. A method only ever is supposed to output once. But if A is a number larger than is larger than 1, then it's going to fail this check. So it's going to move on. And then it's instead going to go through each of these two methods, where we're going to, the value we want to return for this Fibonacci method is the Fibonacci method of the number 1 smaller than it and the number 2 smaller than it. Or not specifically, if we want the Fibonacci number, the 5th Fibonacci number, we would simply call Fibonacci 5. And what this and so what this would do is essentially, if we want to find the fifth number in the Fibonacci sequence, in order to find that, we first have to find the 4th number, because 5 minus 1 is 4. So in this case, this method will find the 4th Fibonacci number and the 3rd Fibonacci number, since 5 minus 2 is 3. And then we'll add those together. But since the computer doesn't know what the 4th Fibonacci number is, it'll this method, when it calls itself, will then find the 3rd and 2nd Fibonacci number. And then it'll keep calling itself until it reaches 1 or less. And then it'll return 1 and then recursively go through all those steps. So in other words, when if we run it as an example, So you can see when we run it, it's gonna go into the code because after you call the method and give it the input, it's gonna run inside, go to this method and start running it. So it's gonna see the first check and it's gonna fail it because a is not less than or equal to 1. It's greater than. So it's gonna be the next step, which is going to go to return the Fibonacci, return itself, return its own method, but with a different value every time. So it's going to go inside the first Fibonacci because that's first. It's going to go inside the first Fibonacci first. And now because the new value is a minus 1, so it's going to go to the value 4 first. And then it's going, and then for 4, when we run Fibonacci and put a 4 as input, it's going to call itself twice. But instead of calling itself with a 4 and itself with a 3, it's going to call itself with a 3 and a 2. And it's going to call Fibonacci again, but this time with a value of 2. And it's going to call itself again, but this time with a value of 1. And since this time this function is true, it's going to return just 1, which is the first number in the Fibonacci sequence. Essentially, it's a recursive method. We define the base case, which is when Fibonacci is equal to 1, return the first value, which we know is 1. And the recursive formula is simply the previous value plus the value before that. And then the program is going to keep running through all of the Fibonacci sequences that's created. All the way until we get back to 5. And it'll give us the 5th number in the Fibonacci sequence, which is 5. Recursion is extremely powerful because it's sort of like, because the way it repeats itself can be incredibly powerful in solving various questions. Simply put, even if you have no way to because it allows you to solve a question by knowing only 2 pieces of data, which is the beginning case and the formula for each successive case, where each following index is dependent on the numbers before, which allows us to calculate Fibonacci pretty elegantly. Because Fibonacci is always equal to the 2 previous numbers, you can simply tell the program, okay, find the 2 previous numbers. For each of these numbers, find the 2 previous numbers. And for each of those numbers, find the 2 previous numbers until you reach 1 and 0, which we know, whose Fibonacci values are just 1, 0. And then from those, keep adding them together until you reach the current number. And this is how quick search works, which essentially uses recursion to go through all the numbers a bit faster than bubble sort. Now, the problem with recursion is that it's kind of slow because, as you might have noticed, especially if a number gets really big, this will repeat a lot of times. And while that's not a problem mostly, the problem lies in the fact that this will often repeat itself. Like, for example, you might have noticed in the Fibonacci we talked about earlier, when we call 5, it'll call itself with a 4, itself with a 3. But when it calls itself with a 4, it also has a 3 inside it. So in other words, we calculate the Fibonacci of 3 twice, when really we only need to calculate it. If we could calculate just once, we could then replace each time we calculate a future value 3 with the value that we already found, instead of having to repeat it every single time. So the problem with recursion is that you often repeat steps that you don't really need to, which is often why it's super slow and why you only want to use it as a basis. Specifically, something like dynamic programming, which does exactly what I just said. It's recursion, but you store the case you solve. So if you ever use it again, you don't have to resolve it. And it's much faster, and it's often like the pillar of both competitive programming and a lot of just general programming as well. But yeah, recursion is an extremely powerful tool, especially if you can get it to work fast, much faster. And it allows you to sort of like a for loop, do repetitive functions that can lead to an answer. All you have to know is the base case and how to calculate each previous case. And again, and recursion is also an important way of finding various other functions like the aforementioned quicksort. Oh, that's not person. So specifically, quicksort works like this. So it looks like this. In quicksort, we choose a random element called a pivot. It doesn't really matter which one it is. You can pick the middle element or the first element. It doesn't matter. And in order to sort the list, we have to first pick it out. So we'll just say, in this case, we'll make it the middle of the list. And this index is going to be our pivot, or in other words, the place we rotate things around. So after we take a pivot point, we'll divide the list into two different lists, one of which contains all the numbers small in the pivot, other ones contain all the numbers larger. In other words, when we pick a pivot in the middle, all the numbers bigger than it get pivoted or rotated to the other side. And any numbers that are larger on it on the other side will rotate into the large list. And for each of those lists, we'll repeat. So this can be accomplished with the recursive function. So first we pick set our pivot point and set the beginning point of the sublist we're going to look through. And then we're going to iterate through each of the elements in that sublist. All right, so all right, so as you can see here, what we've essentially done is we first go through each this I should probably rename this method something else. So this method takes in as input an array and two numbers, the beginning and end of the specific sublist that we divided the list into. And we set the pivot to the ending point and set I to the beginning point, to the beginning point. And we loop through the entire list, this entire sublist from 0 to this ending point. When actually this should to whatever it should be, to beginning to this endpoint, increase by 1 at a time. And if the value is ever less than or equal to pivot at what we're looking for, then we swap it around the pivot. And then at the very end, we swap the temporary point one more time as its new pivot, and then we return I+1 here. So essentially, the way this is supposed to work is given an array, let's say if we pick 5 as our first pivot, then we put all of the elements less than 5 in the first position of the array. So in other words, 3 and 4 all get put into the first position of the array, which is supposed to happen with the swap here. Becomes 3, 4, 5, 9, 6, 5. And then we'll repeat for the subarray before 5, which is 3 to 4, which is what the int begin int entered for. They establish the beginning and end of the sublist of the specific subarray of the original array that we're looking for. So if we're looking at just 3 and 4, that would be swapped to the beginning. This would be say 0 and 2. And we would swap those if necessary. And then we would go to the right side, which would be 9, 6, and 5, pick a pivot there, and then swap everything around. Say if we picked 6, we would swap 5 one and 9 to the other. And then we would check 5 and 9 itself, but because they're both a single number, the check would be really fast. Since they're just to be a single number, they would already be optimally sorted. So that's quicksort. There are lots of other sorts that you should probably look at. Quicksort is just one of them. There are other things like the merge sort I talked about earlier and the other various ones. It's just that quicksort is the one we're going to talk about today. A lot of this stuff is very much stuff you can, very much stuff you should probably learn by yourself if you want to do coding. And since most of these ideas borrow on each other anyway. The next thing we're talking about is basically various form of data structure. Specifically one more way of storing data. We already know about arrays, which is simply one here, where you give it a specific set size and a specific element of data to hold. And one we haven't talked about a lot is array lists, which are very similar to normal arrays. The main difference is they don't have a set size, and you can keep putting in new elements, and it'll change the size to reflect that. In other words, it's the default case, its array size starts at 0, and every time you add an element, it'll essentially create a new array that has an extra space to fit in that new element. And because it's an object rather than a simple primitive array, it has various methods attached to it that you can also use that the normal list doesn't. For example, instead of having to manually implement a search in a normal list, you can also use the array list has its own contains method, a remove method, which will remove the object or the index or the object at the index, and also has various other methods like changing the list array from an array list to a normal array, or adding an entire list to the array itself. The big problem with the array list is that compared to normal lists, they're much slower because they have to account for the fact that they can hold any number of variables. And yeah, the next important data structure to know is sets and maps. So sets is essentially like an array list or an array, but they cannot contain duplicate values. If you try to give it a duplicate value, it'll just reject you. So specifically, a set is a collection of unique values. So Java, this would be yeah, in Java, they're called hash sets. And so a set is essentially a data structure that's very similar to an array list, and it's also an object, and that its size can vary, but they will only contain unique values, which makes them ideal for situations where you say only want one of every value, or if you want to know when there is a unique value or not. And like arrays, they also have various methods they can use. They have the basic add method, clear method, contains method, etc. This specific type of set is known as an unordered set, which is essentially just a set. So it's all unique values, but it's unordered, or the elements are put in whatever order you put them in. It doesn't randomize it. Rather, it's simply the only way to make it like in an ordered way is if you manually import each element in the correct order. And sorted sets, as the name implies, the elements would be sorted in order, which in Java, instead of a hash set, you would use a tree set rather than a hash set. The difference between the sorted set and the non-sorted set is that in an underordered set, it takes one operation to insert an element, delete an element, or search for an element, while in a sorted set, it takes a log n amount of time, which basically means it takes a bit more time than the unsorted set does. But the main function of both these sets is that they're meant to contain unique values, either sorted or unsorted. And the second important data structure to learn about is a map. And maps are data structures where they contain each element they contain is two values, a key value and a value, where in order to access a value, you have to know the key. In other words, in that essentially, you know how int lists, arrays in general, in order to get an element, you have to know its index. In a map, instead of using a number as index, it uses another object as an index. So in other words, technically speaking, a normal list is already a map. It's just its key value is always an index, an integer. So this specific map data structure, it holds a double string value, where the first value is meant to represent the key or what you use to find what the value. And the second value is the actual value, like the actual type of value that's being stored. So if I want to ever add something to a map, you have to put in a key value, and then an actual value. In order to access it, instead of looking for index or iterating through the list, you have to actually use use the key value that you set for the list, which in this case is just key. So if you want to extract the treasure value, you would have to input in key. It's not really meant, this specific thing isn't meant for security because there's a bunch of methods that's meant to help you search through it. For example, there's a method called key set, which is the set, which creates a data structure called set, which contains all the keys, and you can just loop through that to find all the different key values. The main purpose of a map is to pair things together, where say, if you were trying to pair all of the roads with a specific city, then what you could do is you would take a key value, which is the name of the city, and then a string list value. So in this case, we could put like the city of Paris, and then we would give it a new string value. Or the key would be this name of the city, and then it would be paired with a string list that contains, say, the name of the lists, the name of the roads, and like what the lengths are and stuff. So maps are essentially meant to pair two things together to easily identify them. So essentially, if you want to know how many roads Paris have, they'd probably be stored in a map, where the key Paris, the city, is stored with a string list containing the different roads and stuff, pairing them together, essentially. Similar to sets, the key values must also be unique, because if you ever had a duplicate key value and then you try to use the key to find the specific value, the program wouldn't know which of the keys we're looking at. So all the keys have to be unique. If you try to put in a value that does not have a unique key, it'll throw an error at you, and it'll just simply refuse to do it. However, the values don't have to be unique, since the values every value is technically already unique in that they're paired with a unique key. So no two while the value itself might be the same, the identification for every value would be different. So the values itself wouldn't be a set. They could still be unique values. I mean, they could still be common values that are shared between keys. For example, in the road example, roads connect two places. So when you put down to each city, the cities probably have overlapping roads with each other. Yeah, so essentially the four main data structures are normal arrays, which have a defined size, but are generally fast to make, and you can loop to them, and any operation you do with them are fairly quick, but their size is limited. So in order to, if you wanted to create any array with a larger size, you have to reset it by creating a new array with a bigger size. Array lists are essentially just the previous arrays, but now their size is changeable. And because it's structured as an object rather than a primitive value, it has lots of methods to go with it that allow for more functionality. And essentially, you don't have to code it all yourself. There are various ones that are automatically coded for you. Sets are like array lists in that they have a variable size and can store various values, but they have to have a unique value. If it's ever unique, it'll throw you an error each time. And for maps, they're again similar. They can hold any amount of data that they can change. It doesn't have a set limit like an array, but it uses two values, and each time you put in a value, it has to be a key value pair where keys are unique, but the value does not have to be. So, and these are the main four important data structures. Any other piece of data you might need to store, like say a graph or something, can usually be stored in some variation of this. Like if you wanted to store a graph of points, you would probably use a 2D array or 3D array, depending on what like dimensions the points are in, and you store it like that. If you wanted to store the aforementioned city, road pair, or any other paired objects, you might want to use a map. And sets are for when you store specifically a group of unique numbers or strings that might say that you need to easily know when to identify, like when they're not unique, or if you simply know they're already unique, because that allows you. This also allows you to search much faster than array lists if you know the values are already all unique. And the difference between hash set and tree set here is that this one is unordered, so any element you put in there doesn't automatically sort each time, but a tree set will automatically sort each time. Okay. So yeah, those are the various different data structures. Another important thing to keep in mind while programming, and this one's more of a structure thing rather than actual programming, rather than actual programming object. This is more of a thinking way. It's called, essentially you want to structure your algorithms to be as efficient as possible, because you don't want to waste time doing repetitive searches or anything. So one way to do this is by implementing greedy algorithms, which essentially just always check the highest value first and move on to the next. Like, for example, oftentimes, say in a program, you want to know how to make the smallest set of coins. Like if you had a sort of if you had a list of coins to use, and you were told to say buy something of those coins, and you want to use the least amount of coins possible, a greedy algorithm would be most efficient. More specifically, let's say you had a coin list of 1 cent, 5 cent, 10 cent, and 20 cent coins, and you wanted to construct the total sum of 106 cents. you could say go through every single combination of coins that add up to 106 and simply find out the one with the least number of coins used or the maximum number of coins used, depending on what you're looking for. But you obviously don't want to waste time. So greedy algorithms are essentially a really good rule of thumb that work for almost everything. And it simply just goes start with always the highest value first. So in other words, yeah. So essentially, in this algorithm, we create a temporary sum that's meant to represent the current sum that the program is at, and the number, which is supposed to represent the number of coins being used. And so we create a very simple program where we keep repeating it until this temp sum is equal to this sum. And then we simply iterate through all the coin lists, starting with the largest value. Because after all, if we can use a 1 cent coin or 5 cent coin, 10 cent coin, chances are it's always better to use the 25 cent coin first because it is the most value and thus would be the fastest way to decrease the number of coins you use. And so we simply just check that doesn't go over the limit because we don't have a negative coin. And if it doesn't go over the limit, we add it to the temp sum, increase the number, and then we immediately break because we don't want to use the rest of the coins. We want to always make sure we're using the maximum value coin unless absolutely necessary. And so essentially, a good rule of thumb in programming is to be essentially greedy with your algorithms, to go for check the largest value first, or simply check the most likely cases and then followed by the least likely cases. Like if you wanted to check, where a person's clicking, you probably want to check the largest clickable area first, and then each successive area after that, in order to allow your program to save time and memory instead of having to check cases that are much less likely to happen. Yeah, that's based if you for that next 5 minutes class, I think I'm gonna just reserve our questions since this is the end of the class and all. Does anyone have any questions to ask? Anything they want to clarify, or anything they simply want to know more about coding? Anything they think they might have missed? All right, so that's basically all. That's it. All you need to know how to start coding. Obviously, there's a lot of information that that's like still out there, but a lot of that stuff is either very specific or stuff you probably won't encounter for some time. Through these classes, we've learned how to go through inputs, do outputs, do operations, and even how to make an actual like visual frame pop out. And today we've talked about essentially the various formulas and stuff that are most commonly found in programming, like recursion and greedy algorithms. Most important to have for you, though, is essentially remember that the internet is like the birthplace of computer science, especially today's modern computer science. everything you ever want to know about it is going to be stored on there. And while this class is a great introduction to being able to code your own programs, a lot, even actually veteran programs do this a lot of time. And sometimes lots of other programmers don't even consider you an actual programmer until you've gone onto the internet and like look stuff up for the first time. So one thing I always remember is there's usually an answer, there's always an answer on the internet, and you need to learn how to be able to find that answer. So if you want to, if you want to learn outside of this class, now that we're about to approach the end, the various sites and stuff you can go to for tutorials. You can obviously for your own, but for the best spots for Java specifically, there are two main websites that would be best to know more. One is the docs.oracle.com. This website is essentially documentation of more or less every Java method class that happens in the code, every single library class code. So and it comes with the explanation about their inputs, outputs, and operations as well. This is essentially the dictionary of Java. It's Java's dictionary. And so if you ever kind of come across something that you don't remember what it's for, if you just don't recognize it, this is a dictionary that you go for. It's like English, but for programming. And the other website I can recommend is Stack Overflow, which is more like a forum area that's almost exclusively used by programmers. And since computer science has been along for a couple of decades, there's oftentimes, if you ever get like an unknown error or something, or simply working through a various coding question, you can often just search it up on the internet, and one of the first results will be from Stack Overflow, with someone else already struggling with that question. But of course, since Stack Overflow is not like a officially moderated by the developers of Java or something, it's a forum area, the answers and questions will vary slightly. And oftentimes lots of people will, and again, it's a public space that's anonymous, so it comes with all the risks and stuff that entails. But it's used enough that there's lots of coding questions already on there, and most answers will usually contain their example to go with it. Finally, another good spot for like future programming stuff is this website here. USACO is a computer programming competition website, but they have a guide that's also fairly useful to look at. This guide isn't, you definitely shouldn't look at this guide until you learn how to program, but that's what these classes are for. And as long as you have a basic knowledge of what to do, you can also take a look at this guide to learn specifically competitive techniques that can still be used inside non-competitive programs like games. Well, we only have 15 seconds left until 6 p.m. So that's it for this class. I'll upload the last two, this class and the last two onto the Google Classroom when it's over. So if you have any questions, you stay behind, but otherwise we can end it here.